Okay, so let me start by thanking the organizers for giving me this opportunity to speak here. So I'm going to talk about a quite well-known problem in non-equilibrium statistical physics. This is the question of presence of long-range correlations in systems outside equilibrium. So the idea is that we know for systems in equilibrium, the quite well-known problem in non-equilibrium statistical physics. This is the question of presence of long-range correlations in systems outside equilibrium. So the idea is that we know for systems in equilibrium, the spatial correlations are long-range. It's quite common. It's not always, but it's quite common that one finds that the spatial correlations are long-range. So this has been studied quite a lot, particularly in the 1970s. There were some experiments done where they also found this long-range correlations in non-equilibrium stationary state. And then there was a work which is quite well-known now, is by Herbert Spohn in 1983, where he essentially showed that even for a system where there is only one conserved quantity, one could find long-range correlations in the fluctuations of that quantity when the system is outside equilibrium, particularly in the non-equilibrium stationary state. And after that, there were several other works, particularly in the 90s, especially this work, this paper by Garrido, Leibowitz, Christian Mice, and Spohn. That's quite nice. And more recently, there are actually many other works, but some that I know are work by Bernard and Viviane Lecomte. And we also did some work with David Mukamil and Satya Majumdar on this long-range nature of the correlation. So typically, the idea is that, so what I'm going to talk about today is that all these works that has been done, which are often for specific models, I'd like to understand how one could see this from a more general perspective for systems for diffusive systems, which are in non-equilibrium stationary state. Okay, so that is the idea. So these could be understood in a very simple setup, and most of the calculations are rather straightforward. So I'll try to go slow, and if there is any point things are not clear, just let me know. Okay, so let me then start by saying exactly what is the problem that I'm interested in. So I'm going to look at one particular type of problem, not all the non-equilibrium stationary state. So the picture that I'll be studying is this following, that I have a diffusive system, and I couple with, so it's a particle transport system, and I couple with two density reservoirs. Okay? And I then wait, and after a long time, the system would reach a non-equilibrium stationary state when rho A not equal to rho B, and then there would be density fluctuations. Okay? So by diffusive, what I mean that the system follows a fixed law. So by that I mean if I look at the average number of net particle flow from left to right, then this, so up to time t, so this is also called as integrated particle current, and this would follow something as a fixed law. Okay, so this is the conductivity, and then this is where rho A minus rho B is small, and rho is of the order of rho A, rho B. Okay? Now, given this kind of systems, what I'm interested in is that particularly what are the spatial correlations of density fluctuation, and not particularly just the spatial correlation. I'm more interested in even the multi-time correlations, okay, of the density fluctuations. So this is what I want to find. I also want to look at the current fluctuations and multi-time current fluctuations. And moreover, after that, what we will be interested in, not just two-point correlation, I would like to study whatever higher cumulants, so n-time cumulant, and particularly to talk about what are the large deviations, both in space and time, okay, for these kind of diffusive systems. Now, you could very easily see that this could be actually also applies for systems of energy transport, so where this kind of laws are known as the Fourier laws. And also these kind of multi-time correlations plays quite an important role in studies of non-equilibrium systems. So particularly, one finds Green-Kubo formulas where one writes conductivity in terms of integrals of two-time correlations of current. Then there are also cases where one studies linear response theory, which says that if I have a system, and let's say it's in a stationary state, and then I make a small perturbation, and I look at some change in some observable due to this perturbation, then there is a linear response theory which tells that the response function could be written in terms of two-time correlations of these fluctuating quantities. Okay? So in that perspective, studies of these multi-time correlations plays a quite important role in non-equilibrium statistical mechanics. And even more recently, there has been studies of anomalous transport, mostly the framework that is devised by Herbert Spohn, where people often studies these kind of multi-time correlations. So I just wanted to make sure that, make this point that studies of multi-time correlations are important topic. Okay, so before I get into our results, I'm going to just present two of the well-known results which is relevant for this discussion. Okay, so one of the, yes. Precisely. So if you have the large diffusion function, you do a Taylor expansion. And so I will come and I'll really, here, yes, so it's a diffusive transport. Okay, so now I'm just going to just present just two of the known results which are relevant for this discussion. So one of this is the large deviation for the integrated current in this kind of geometry, which just says the following. So this is the known result. So this is the large deviation for this integrated current, so Qt is the net amount of particle flow up to time t. This has the following large deviation form for a large class of diffusive system. So where L is the system length. Okay? This also is equivalent of saying that any cumulant of this current goes as t to the power L, sorry, t by L, it's a linear proportional to t, and then there is a function which is a proportional to rho a and rho b. Okay? And then there is a well-known paper by Bourdieu and Derrida where they calculated this function for a large class of diffusive system, by which they actually showed that, sorry, so here there would be, it's the nth cumulant. So what they showed, that in order to write this function for any n, they will need only two quantities. One of them is defined by the first moment, so it needs the function d rho, and there is a second moment, which typically has this rule. So this is when rho a equal to rho b, so this is an equilibrium. And this function is fully expressed in terms of just these two functions. Okay? So this was obtained by a well-known conjecture, it's called additivity conjecture. So this is the nth cumulant. Okay? So there is a formula for this phi function, the large deviation function. Okay, so there's also been work on the ring geometry, which was done by Vivian Lecombs, and one could derive similarly the large deviation function of integrated current in these systems. Okay, so the second well-known result that would be relevant for us is to look at the density fluctuations. Okay, so this is the one-time property. So what I'm now going to look at is that if I take this system, okay, and coarse grain the system. So let's say I divide, so the total length is L, and I divide into, let's say, k boxes, each of length L by k. Okay, and let's say the Ni is the total number of particles in that ith box. Then this follows a large division form. So N1 by k, and then when I take k large, one could define a coarse-grained density profile, and this has a large deviation form. This is, okay. Now this large deviation function has been so far been calculated only for very specific hand-picked models. So particularly the model where the particles are non-interacting, the model which is known as symmetric exclusion process, and there is a model of heat conduction, which is known as KMP model. Okay? So in these particular models, this psi function, there is a formula for this large deviation function for any rho and rho b. Okay? So these works were mostly done in these rather well-known papers by Derrida, Leibowitz, and Speer. so it's a PRL in 2001. And around the same time, using a different approach, this one was calculated for SEP by Bertini et al. And much later, there was a work by Julia Tailiu, Jorge Kuchan, and Vivian Lecomte. This is also a PRL in 2007, where they, in very different ways, they calculated this function for the symmetric exclusion process. But in these two results, or rather most of the result that is known so far, most of the studies focuses on the one-time properties of these fluctuations. So in this talk, what I'm going to now focus on the multi-time properties. That is the new thing that I'm going to talk about. Okay. So one more comment that I want to make, that from the formulas of the psi function in these density fluctuations, what one finds that this large deviation function is non-local, and which reflects that in the non-equilibrium stationary state, the correlations are long-range. So non-locality of these large deviation function of density fluctuation is related to the long-range nature of the correlation. And if one goes to an equilibrium state, which is rho A equal to rho B, these functions become just a local function. Okay? Okay, so now I just give the outline. So the way I'm now going to present the rest of the talk is I'll first start by an explicit calculation in one non-trivial microscopic model, which is known as symmetric exclusion process. So first I'll do a microscopic exact calculation in SEP, where I will calculate these multi-time density correlations and multi-time current correlations. Then, starting from there, I'll go to a fluctuating hydrodynamic description. So this is a bit phenomenological approach, using which one could address a large class of driven diffusive systems. And then I'll show you from here how one could very easily calculate these kind of multi-time correlations. But then if one tries to, using this method, if one tries to calculate higher cumulants, it gets a bit tedious. So there is a more systematic method, which is known as this macroscopic fluctuation theory. Which is also a version of the well-known Friedlin-Wenzel theory. And using that, one could calculate these kind of multi-time correlation in a rather systematic way. So that I will present towards the end. And at the very end, if I have some time, I'll talk about large deviation function, or rather correlations, when conditioned on some other observables. Okay? So that's how I'll proceed. Okay, so let me start with the microscopic calculation for SEP. And you will see that the calculations are rather straightforward. And one could get these two-time correlations. So how do we do that? So let me first define, most of you know what is symmetric exclusion process. So it's a model on a lattice where each side could have at most one particle at a time, and each particle tries to make a jump to its nearest neighbor with equal probability, so there is no bias. And then I couple at the boundary with some particle jump rate. And these rates would be then related to the densities by a very simple formula. So relate to the density of the reservoirs by a very simple formula. So these are all standard. Okay. So now any configuration of this system is expressed by these occupation variables at any time. And this would take values 0 and 1, depending on whether the site is, ith site is empty or whether it is filled. Okay? Then what we want to calculate is this multi-time correlation. Or I want to calculate these correlations, or multi-time correlations of time, of current. So, okay? So the current, this gives it the net number of particles, or the rate of particles which flow from site I to I plus 1 per unit time. Okay? Okay, so the calculation is rather straightforward. So I'm just going to give you an outline of it, how to do it. Okay. So it just comes from starting with the rate equation. So this is a continuous time Markov process. And one could just write down the rate equations for the averages and the multi-time correlations. And that's rather straightforward. So just to write down, so I'll just write a rate equation. So it's, for convenience, it's easy to write down in terms of like a column vector. So this is a column vector of average occupation. So I start first with the average property. And this has a very simple expression. So usually it is a matrix, which is mostly a Laplacian matrix. So column is 2. And only here, there is some effect due to the boundary. And then this is the same. Okay. So this, we can just as a notation, one could really write down in this very simple notation. So when I don't put an index, it means the column vector as minus m. Okay, so it's just a way up, right? Now, it's a very simple equation, and it's very easy to write down the solution for it. Now, in order to write down in a formal way, I'm just going to write down in terms of a quantity, which is called Green's function. And the reason is that you'll see that all these higher point cumulants could be expressed in terms of the same Green's function. Okay? So this is a really straightforward thing. So I'm just going to define something called a Green's function, which is a L cross L matrix. Which satisfies a very similar equation. So all I just do is that I write G okay, and with the condition that at time t equal to 0, this is just an identity matrix. Okay, then it's really simple just to write down the solution for tau t at any time. And it is simply this g of t if I start at 0, yes, okay? So you can just write down everything in terms of the Green's function. And if I now take t to infinity, sorry, this would be t, then I get the stationary profile. Okay? So this is all straightforward. Now one could now see that one could actually write a similar equation for the two-time correlation. And for this problem, the hierarchy is closed. Okay? So you could write a closed set of equations for the two-time correlation. And one could write a very similar formula for the two-time correlation. So let me just write down the formula. So it's again written in terms of the Green's function. Okay. Okay. One could very similarly, one could write down, again, do the same calculation with starting with the rate equation and write two-time correlations for the current. Okay. So first thing is to here, easy to write down the correlation for integrated current. And the formula is rather simple. So I'm not going to give you an explicit formula, but I'm just going to write how it roughly looks like. So this, I'm now looking at the integrated current up to time t at this bond between I and I plus 1. And this correlation will be expressed as a function of this Green's function and the stationary state occupation variables. Okay. So these stationary state occupation variables are also easy to calculate starting from this rate equation. So everything is straightforward here. Now I'm also interested, as I said, I'm interested in looking at the current correlation and not just the integrated current. So that has a explicit formula. So let me just write, because this will come very soon in the later part. So these are the current correlations. And it has this following form. So there is a delta function. So I just write and then there is this okay. So these functions are again expressed in terms of equal time correlations, which are really easy to explicitly write down. But the important point is to note this part. Okay, so this was a bit unexpected for us when we really derived it. This quantity, gamma, has this very simple form. This is tau I at t plus tau I plus 1 at t minus twice the correlation between just the nearest neighbor site. Okay, okay. So this is what one could get from the microscopic calculation, and one could also extend for the higher point correlations. Okay. Now, what do we gain from this? So by this very simple exercise, the first thing is to note that starting from this, if one gives me this formula, one could rather go to a hydrodynamic scale and obtain this fluctuating hydrodynamic equation rather easily. Okay. So this is something that I'm just going to mention. So what I'm going to look at now, I want to go to a hydrodynamic scale. So first thing that I observe is that how much is the current, it differs from the fixed law. Okay, so I started with saying that the currents here follows a fixed law. The first thing that I'm going to look at, how much at a microscopic level, the current would differ from a fixed law. So for that, I just define this quantity. So yt is the quantity that I'm defining, which is a measure of how much the current differs from a fixed law. Because if you now look at the average current, so this term would give you roughly the fixed law. Okay? So what one could very easily show from this microscopic calculation, that yit average is 0. And what would also find that if I'm looking at two-time correlation, this is simply delta correlated. And this gamma is exactly the same as this one. Okay? Now this is an important relation. And you will see right now very easily how one gets the fluctuating hydrodynamic equation, which one often assumes by starting with some kind of phenomenological argument. So let me just show you now that the fluctuating hydrodynamic equation. So for that, so fluctuating hydrodynamics is defined at a coarse grain level, so where one actually coarse grains over a length scale, which is more than the any correlation length of the fast degrees of freedom. Okay. Right. So so this is the current. No. So right now it's not the average. So I'm just defining Ji as occupation variable. Yeah, these are not average quantities. Only on an average. So if I write down the average current, is the average. Okay. Okay. So now starting from this, I'm just going to go to the fluctuating hydrodynamic description. So what is that? Okay. So this is defined at a coarse grain level. So what I'm going to define now a coarse grain scale where I coarse grain with the total length of the system. So that is, I'm defining. Now I'm going to use a diffusive scaling. So this is S, is my coarse grain time. And then I'm going to use this following coarse graining. So this goes to a density function. Microscopic current goes to, it scales like this. And then I can also see that this difference, the yt, this scales also very similar way, and I define it as this. Now, given this, one could very easily see from that correlations, one would find that the current, what I could write as where average is 0. And if I look at the covariance, This is delta correlated with 1 over L in front. And here, there would be a quantity which is and what from this microscopic calculation, what one could also show that higher point correlations of this eta decays faster with L. So in the scale of order L, one could think of this as just a Gaussian white noise. So this is what one assumes when they start for a fluctuating hydrodynamic description for any diffusive system. So this is one way to see how to arrive for symmetric exclusion process. Okay. Now, given this, I will show you that it's very easy now to calculate all these kind of multi-time correlations. Okay. So there is one easy way to calculate, and there is then a systematic way of calculating all higher point correlations. Let me first tell you the simple and straightforward way how to calculate that starting from this kind of description, how one could calculate this multi-time correlation for a general diffusive system. So for a general system, what would happen that the only difference that would come, that there would be a diffusion constant. Okay? And what would happen that this quantity for a general system would be another function, which is sigma of rho. Okay? So now the idea is starting with this, I want to calculate all these multi-time correlations of the fluctuating quantities. Now, it's quite straightforward to calculate all these quantities. So let me just show you. So the idea is just to start with this fluctuating hydrodynamic description, do an expansion in the weak noise parameter, and that would give all the endpoint correlations. So to start with, what I'm going to define that 1 over L as I'll define it as epsilon squared, where epsilon is small. Okay? So all the calculations are done in the large L limit. So, okay. So how does one do that? So I'm just going to give you the rough idea how to do that. So I start with that fluctuating hydrodynamic equation, and then I just write an expansion in powers of this small parameter epsilon. So the first quantity that I write and then order epsilon square, and so on. Similarly, I could do it for the current. Okay? It turns out that this quantity would satisfy just the noiseless diffusion equation, and it will give you the average profile that's evolving. But then it's very easy to see that if I'm looking at the multi-time correlations of density, so here I change the notation again. I'm using time, but now I'm already in the hydrodynamic limit. So all these variables, x and t, are in the hydrodynamic scale variables. Okay? So this is very simple. It's just epsilon square r xt r ys plus higher order terms in epsilon. But I'm mostly interested in the leading order behavior because that's what would be important in the large deviation studies. So now I only need to calculate this. So what one could first do is just take this formula, put it in the fluctuating hydrodynamic equation, and get an equation for the R, which is a really straightforward equation. And everything here is really simple algebra. Okay? So I'm mostly interested in the correlation in the stationary state. So I'm assuming that rho bar xt, which is the average, is time independent. Okay? Now, given this formula, you can see that you can write down the solution again in terms of a Green's function, which is also really straightforward. So I'm just going to define this Green's function, so which is capital G x, y, t. Zero, with the same thing as x, y at Green's function at time 0 is simply a delta function. Okay? It's a very similar thing, but now we are doing at a hydrodynamic limit, and we are doing the calculation for a more general kind of different diffusive systems. Then it's very easy to write down what's the formula for R, just like in the microscopic case, and then one could calculate this two-time correlations in terms of the Green's function. Okay? So these are really straightforward calculations. So I'm just going to write down just some important formulas, what one gets. So one thing is that one gets a formula for the two-time correlation in terms of the Green's function and equal time correlations in the stationary state, okay, which matches perfectly in the result that one derives from the symmetric exclusion process if one just puts d equal to 1 and sigma is 2 rho 1 minus rho. Okay? So that I'm not going to write. The other point that one finds that one could very similarly write down a formula now for this multi-time correlation of current, and it has exactly a similar formula like here, but only thing that changes is becomes, so now I'm writing in the scale variables, so it would be x minus y, then one gets a sigma of rho y, and then quantities which would just be a scale limit of these kind of formulas. Okay, so the explicit formulas are not so important, but the important point is to note that there is this delta correlation, which we found a bit unexpected. So the other important result is, it's a bit interesting, is to look at how the correlations of the current would look like. Okay, so correlation of the integrated current, because this is something which has been studied a lot. So if I look at that, it has a rather interesting behavior. So if I look at, so I'm defining now the integrated current in the hydrodynamic limit, and this is simply this time integral of the current. And if I look at the two-time correlations, it has this following form. So let's just, for simplicity, I look at the same site, but at the 2 times. This has the following form. So at time, which is much larger than 1, so this in the hydrodynamic scale, that means that in the actual microscopic scale, all times are more than L square. So this has some behavior which is like minimum of T and S. And if I'm at the case where it is much less than 1, then it has an interesting behavior, which has this form. So this would remind you that this is like a correlation in Brownian, and which is expected because beyond that time, everything gets uncorrelated, the current fluctuation, and one would get a Brownian. But what is unexpected is that if you look at it at the short time, it looks like a correlation of a fractional Brownian motion with Hurst exponent 1/4. Okay? Okay, so now I started by saying that I want to look at the long-range correlations. So given this 2-point results for 2-point correlation, what can we say about the long-range correlations? So for that, I'm just going to talk for the moment, only the correlations of the density. So if I look at, so just for the sake of interest, I'm just only going to look at the equal time correlations of the density fluctuation. But now you see the results are for a large class of driven diffusive systems. I'm just going to write down how it looks like. So now I'm looking at the same time correlations. Because in the stationary state, the time doesn't matter. This actually has the following form. So there is a part which depends on d and sigma, and there is a delta correlation. Plus, there is a part which is not delta correlated. Okay? And this part is actually the long-range part. Okay? So how does one see the long-range nature? One could definitely write down this as an explicit formula in terms of Green's function and see that it is long-range. But the interesting way to see it is look at what equation this satisfies. If I look at the equation, so it satisfies something like this, like a Laplace equation. And then on the right-hand side, there is a localized charge. So let me just write down. So if you think about analogy with electrostatics, so for example, if I look at the case where d equal to constant, then this is just like a Poisson equation with a localized charge. Okay? So in electrostatic, then you would, from electrostatic analogy, you would expect that this part will have some power law decay. So for specific models, if you look at if you put the values of d and sigma, you can calculate what is the lowest non-vanishing multipole of this charge, and that would give you what is the large-scale behavior. So for specific problems, one could actually derive those large-time behaviors, and one is done in this paper, and also one could obtain the result that was obtained by Herbert-Spohn for symmetric exclusion process. Okay. So one more important thing to note here, that this is mostly a non-equilibrium feature. So for example, if I have just put the current equal to 0, the charge becomes 0, so the long-range part of the correlation just vanishes. So this is a particular feature for non-equilibrium. And also, if you could just check that if I have non-interacting particles, then this charge, this quantity also vanishes. And also for zero-range process, this vanishes. Okay, so this is just a consistency check. Okay, so now what I'm just, in the next 4 minutes, what I'm just going to give an overview of how all these things, so not just two-point correlations, but actually the all endpoint correlations one could derive using a more elaborate framework. So that I don't have much time, so I'm just going to give roughly just a sketch of it. So this framework is this macroscopic fluctuation theory, so which essentially says the following. The idea is that one starts with this fluctuating hydrodynamic equation, and the picture is that in a very schematic phase diagram, so if density and the configurations are evolving with time, and it's taking many different paths. Okay? And let's say I want to observe a certain density at the final time. Okay? And that probability one could write in terms of an action. So let's say I want my density at a final time, so let's t final, to be Rx. Then what it appears that one could actually, starting with this fluctuating hydrodynamics, one could write this as a path integral with a certain action. Okay? So this is a bit technical, but I don't have time to explain this. But what one usually finds, so you are looking at all possible paths which ends at this final density profile and with this action. Okay? And then, if we are expecting that there is a large deviation form for this density profile, it would simply be in this integral, the dominant part, which would be just governed by the minimal of the action. So this would simply be minus L S min. Okay? So then, essentially, the large deviation function is just the minimal of this action. Okay? Now, there are many technical ways of deriving or minimizing this action and calculate all these different kind of correlations. One could easily generalize not just for one-time properties, but also for multi-time properties. But let me just very quickly tell you how one could arrive this kind of equations for any endpoint correlation. So for that, one has to start with this following thing, which many of us probably have studied in classical mechanics, is that if we are looking at this least action path, or to calculate the minimal action, there's a formalism which is known as Hamilton-Jacobi formulation, which immediately writes an equation for this minimal action itself. So if I use that, then it essentially writes down to a formula which is something like this. So in the stationary state, it's a formula like this, where H is an effective Hamiltonian associated to this action. Okay? Now, once I have this, I could actually write down equation for all these endpoint correlations. And that one could do in just in 2 steps. The first thing is to note that any endpoint correlation comes from an expansion of the cumulant generating function, which is simply a Legendre transform of this. Okay? And that cumulant generating function, if you write lambda, this is just a Legendre transform of this phi, which will satisfy this kind of equation. R lambda minus phi over dx. So that would make a relation between del phi del r. So usually what would happen, that del phi del r would be lambda, and r would be del mu del lambda. So I just substitute this in this equation. That will give me an equation for the mu, which is the cumulant generating function. And then all I need to do is to take this equation and expand the equation in orders of this fugacity parameter lambda. Okay? So if I do that, then one gets the following type of equation. at every order of lambda. So this is a bit technical, but I'm just giving you an overview. So if I now look at any n-point correlation, okay, and I look at first an expansion of this quantity, then I will get some kind of Laplacian operator acting on the nth cumulant minus some kind of charge, and then I have lambda x1, lambda xn equal to 0. So because the fugacity parameters are all arbitrary, one gets an equation which this quantity, this equal to this. So this is a nth cumulant generalization of the equation, the Laplace kind of equation that I showed here. Using that, one could really see that there is long-range correlation for any n-point correlation. And in fact, one could actually write down in a rather explicit formula in terms of, again, the same Green's function that I have introduced. So this is one important point that I wanted to make, and then I finish, that I started by telling you that for the case of density large deviation, so far the results were available only for symmetric exclusion process, KMP, and non-interacting. And the question what one wanted to study is there a way to write down this large deviation function in term for any dn sigma? So this procedure actually says that one way, one could at least in a formal way, one could write down these large deviation function in terms of this Green's function that we have defined here. Okay, so this is still a formal expansion, and everything is written in terms of formal integrals. Now, what one needs to do is to pick up some specific model and really look at this formal expression and write in a more compact formula. So that's so far what I had to say. And so I don't have time anymore to talk about this other other problems, which were to study multi-time correlations of also of the current and also of the integrated current, which all could be formulated in terms of this variational formulation. And also one could then talk about joint distributions of the density and the current. And one could also talk about large deviations, which were conditioned on some kind of other observables. Okay? So these are some work that we are still doing, and hopefully in a few months we'll be able to publish on this. Okay, so thanks for your attention.
Any questions?
How density correlation is not local directly implies that there is a long-range correlation.
You mean that why the large deviation function is non-local means density function
right.
is...
Yeah.
So what it turns out that this way, that, what I didn't manage to write is that if you look at something called a Legendre transform of the large deviation function, okay, so which is this mu of lambda x dx lambda x rho of x. Okay. So this is the Legendre transform, so you would maximize or optimize over rho of x. Now this quantity has a formal expansion in terms of lambda. Okay? And it turns out, using that one could show if I'm looking at any nth point, or let's say just 2-point correlation, for example, x2, this would be two functional, second-order functional derivatives of this lambda. Okay. So it turns out that if the phi function is non-local, then mu is also non-local. Then if it is non-local, then this derivative will depend on both the functions x1 and x2, and there is no delta correlation. Okay? So if it was short range, it would have been just a delta correlation. Okay? But just because of the fact that mu is now non-local, it's not a delta correlation, but it has a dependence on x1 and x2, and that is the long-range part of the correlation.
But even if you have simple exponential decay with certain length scale,
right? So we are
call it short range.
So we are now in the hydrodynamic scale. So all those, so the scale is this hydrodynamic scale is defined at a scale which is larger than those short time correlation lengths. So any of those exponential decays are contained in these delta functions. Okay.
This sigma for the microscopic model.
Right.
So if I just naively try to generalize, it looks like grad rho square average, right? Because tau square average is same as tau average.
Right. So this is
here it's something else, no?
You mean this quantity is
like tau I minus
average.
tau j
So it's a tau minus tau I plus 1.
square average. So it's like grad rho square average, right?
Yeah. No, this is not
Like that, I can that tau I minus tau j can
So you can,
grad rho.
yes.
But here it looks like rho into 1 minus rho, no?
Right. So
where is this?
So I don't know how. So the point was here. So this part will be like rho of x. This part will also be like rho of x. Okay. Plus some term which is of the order of 1 over L. If I do this expansion,
Yeah.
this will give you. So I'll have tau. So I could write down this as this. Sorry, this quantity. I just could write down as minus the connected part, and connected part goes as 1 over L. If you just write
I
down.
understand, but I could have started with that other one where it's tau I minus tau.
So I'm sure that in the algebra somewhere it will stop because this is the correct result, and I just have to sit down and see where it would fail.
So if, like, supposing I have a bunch of particles in one dimension with some interactions and with overdamped Brownian dynamics.
Yes.
With some, let's say, short-range interaction.
So that's the Dean's equation that will follow.
Right, yeah. So if it's non-interacting Brownian particles, then you get sigma equal to rho, right? And then there's no long-range correlation.
Right. No, so you get sigma equal to rho, but you would get the diffusivity would be different. If you take the Dean's equation, the diffusivity is not 1. It's something which depends as a function of the interactions.
Right, yeah. No, I'm saying if it is non-interacting, then of course D is 1 and then you get no correlation.
Yes.
But is there an example where with some correlations you can actually get, there's some known answer for some interaction?
So that I don't know of right now, but it will, as long as, so if you start with the Dean's equation with any D, this formula will still hold. Okay?
Just given the interactions, typically I don't know what to right?
Right.
Just asking, is there an example with some interactions?
So that I don't know, but when one gets the fluctuating hydrodynamics in Dean's equation, it has an expression where we could probably interpret some part as a diffusivity. It has a fluctuating hydrodynamic equation, right, in the Dean's equation. So I don't remember it immediately how the exact form is, but what I roughly recall that there could be a D which would depend on the interaction that you put amongst the Langevin equations. But also, I want to make a point that this analysis, one could also do it if you have also a drive term in it. So in the fluctuating hydrodynamics, if I put another term, you could still do the same. And you can actually write down in a similar explicit formula. So this analysis is rather straightforward and very easy.
Other questions? If not, let's thank Tridib again.